Welcome to Lecture 5 of the course Wireless Communication at Chalmers University of Technology. My name is Henk Wemiers. In this lecture we will cover part of Chapter 6 of the book Wireless Communication by Andrea Goldschmidt, and we will focus on different error metrics for fading channels, including outage probability and average error probability. We'll also talk about differential encoding and detection. These are the learning outcomes for today. You should be able to distinguish between different SNR metrics, compute outage and average error probabilities, and describe the difference between coherent and differential detection. Last time we talked about the wireless channel, which can vary in time and in frequency. We also introduced notions of coherence time and coherence bandwidth. We saw that the channel has essentially three components: path loss, shadowing, and multipath fading. Path loss is the decay of power with distance. Shadowing are large-scale power variations due to large objects. And multipath are small-scale power variations due to small changes in the environment, on the orders of a few wavelengths. The channel itself is random. It varies over time and has a specific autocorrelation function. Shadowing and multipath are random with specific distributions. Shadowing being log normally distributed, while multipath fading we have seen Rayleigh and Ricean distributions. We've also seen different kinds of autocorrelation function. This is the autocorrelation function shown in green under a widespan stationary and uncorrelated scattering assumption. This autocorrelation function has two arguments, the delay tau and a time difference delta t. Letting delta t go to 0, we find the power delay profile from which we can read off the delay spread. Taking the Fourier transform of the power delay profile, we find this autocorrelation function, AC of delta f, which tells us how correlated two different frequencies are. From this function we can read off the coherence bandwidth. Due to the Fourier relationship, it must be so that the coherence bandwidth is approximately 1 over the delay spread. By looking at this autocorrelation function, which is obtained by looking at the original autocorrelation function and taking the Fourier transform with respect to tau, and then letting delta f go to 0, we find an autocorrelation function that only depends on delta t. From this, we can read off the coherence time. Taking the Fourier transform of this latter autocorrelation function, we find the Doppler power spectrum, from which we can read off the Doppler spread. It then follows that the Doppler spread must be 1 over the coherence time, approximately. We also found this last function called the scattering function, which is obtained by taking the original autocorrelation function and taking the Fourier transform with respect to delta t. We see there are different paths to reach each autocorrelation function, so we can go down this path, or we could go down this path and obtain the same function. We've also seen the difference between the channel and how we communicate over this channel. With the channel, we can associate a certain autocorrelation function under the widespan stationary uncorrelated scattering assumption. From this autocorrelation function, we find 4 new functions, shown here, which are 2 by 2 Fourier transform pairs. From the first autocorrelation function, AC of tau, the tau for which this function is close to 0 is called the delay spread. From the second autocorrelation function, AC of delta f, when this is close to 0, we can read off the coherence bandwidth. Since those two functions are Fourier transform pair, it follows that the delay spread is approximately 1 over the coherence bandwidth. Similarly, the delta t for which the autocorrelation function AC of delta t is close to 0 is called the coherence time, and the value of rho for which SC of rho, the Doppler power spectrum, is close to 0 is called the Doppler spread. Since those last two functions are a Fourier transform pair, it follows that the Doppler spread is approximately 1 over the coherence time. This is one part. On the other part we have engineering, which involves choosing a certain bandwidth or a certain communication symbol slot to communicate over this channel. When our bandwidth is much smaller than the coherence bandwidth, that means the channel will be flat. That means there will be no intersymbol interference. This is equivalent to choosing a symbol slot that is much larger than the delay spread of the channel. So that means, again, there is no intersymbol interference. On the other hand, when we choose a bandwidth greater or equal than the coherence bandwidth, or equivalently a symbol slot smaller than the delay spread, then there will be intersymbol interference. This is called wideband or dispersive or frequency selective communication. On the other hand, when we choose a symbol slot on the order of the coherence time of the channel, then each symbol will see a different channel realization. This means that we will have fast communication. This is the same as a bandwidth on the order of the Doppler spread. On the other hand, when we choose a symbol slot much smaller than the coherence time, then we have slow communication because the channel will not change for many symbol slots. This is equivalent to having a bandwidth much larger than the Doppler spread. In most communication systems, we want to have slow communication. This means that the channel is approximately constant for some time. As a consequence, because for slow communication we need a large bandwidth, this also means that we will typically operate in the dispersive regime. So most practical communication systems are wideband or dispersive and slow fading, so that the channel remains constant for some number of symbols. The next 3 slides will be a brief review of baseband communication over an additive wide Gaussian noise channel. Here we consider a traditional baseband signal comprising symbols AK drawn from some constellations such as DPSK, pulses P of t with a certain bandwidth B, and a symbol slot duration Ts. The received signal is then simply U of t plus additive wide Gaussian noise. The signal itself has a certain power, PR, and the noise has a certain power spectral density, N0 over 2 watts per hertz per real dimension, so in total N0. The receiver will then apply a matched filter matched to the transmit pulse, which, if it is well designed and we do synchronized sampling, we obtain an intersymbol interference-free observation Yk. Yk is a complex number equal to the transmitted symbol up to a scaling and noise. This noise is just traditional complex Gaussian zero mean variance N0. We can then define 2 signal-to-noise ratio metrics, the analog version, which is the received power divided by the noise power spectral density times the bandwidth, or the digital version where the SNR is the ES, the energy per symbol, over N0. These two are in fact equal given that Ts is a constant over the bandwidth. We have 2 notions of SNR. We will denote by gamma S the SNR per symbol, so ES over N0, while gamma B will be the SNR per bit. This is because a symbol can contain log 2 m bits, so the SNR per bit is smaller than the SNR per symbol. This is also given by the energy per bit divided by N0, where the energy per bit is the energy per symbol divided by log 2m. The performance of a certain modulation format over the additive wide Gaussian noise channel depends, in terms of symbol error rate, on the number of points, the modulation format, and the SNR, or in terms of bit error rate, the modulation format, the modulation size, the mapping of bits to symbols, and the SNR. As a side note, please note that the notation gamma here is used to denote SNR, while in the first few lectures it was used to denote the path loss exponent. I hope this will be clear from the context. Given a certain constellation, we can often derive the performance of this constellation in terms of the symbol error rate. So for DPSK, the symbol error rate is given by these 3 expressions depending on the value of m. For many constellations, including DPSK, the symbol error rate can be well approximated by this equation here, where the symbol error rate is a constant alpha m depending on the type of constellation and number of points, a Q function, then a square root with another number bm, beta m, and the signal-to-noise ratio. For PSK and QAM with gray coding, we can also derive an approximate expression for the bit error rate, which is a symbol error rate divided by the number of bits per symbol. So it can be useful for exercises to take this expression in mind, which here is shown for many different kinds of constellations, including BPSK, QPSK, PAM, PSK, MQAM, rectangular and non-rectangular. So the left column shows the symbol error rate, which is all of the same form, a constant times a Q function times square root of SNR with another constant inside, as well as the approximate values for the bit error rate. We now move on to the performance of the flat fading channel. On the right hand side we show a figure where the y-axis is the received power, which is a measure of the SNR in fact, and on the x-axis time in seconds. We also know that we pose a certain threshold value here. We then consider 3 cases on the duration of the symbol slots. When the symbols are very, very short, as shown here in red, then many symbols will see here a good channel, or if you're unlucky, many symbols will see a bad channel. When a symbol slot is much larger, as in the green case, then different symbols will see radically different channels. The symbol here will see good channel, the next symbol may see bad channel, then a good channel again, and so forth. Finally, when the symbol slot is extremely large, as shown in yellow, then during the duration of a symbol there will be many different channel realizations, so many different SNRs. The model in all cases is the same. The received signal is the channel as it varies over time, a complex number, U of t, which is the sequence of transmitted symbols with a pulse shape, and N of t, which is additive Gaussian noise. We then have three performance metrics for communication over a flat fading channel. First of all, outage probability, the probability that the SNRs falls below a threshold. So here we had a threshold of minus 10 dB. Let's say in red we have different data packets. When the SNR falls below minus 10 dB, maybe the receiver cannot decode the packet. And then we declare an outage. So this is a bad event. In this case, here the channel was bad, the channel was in outage. So we want this outage probability to be as small as possible. Another metric is the average error probability, which is defined as taking the instantaneous error probability for a specific SNR and then averaging over all possible SNRs. So PS of gamma is the error probability for a specific SNR, P of gamma is the density of the SNRs, so then this is the average error probability. We will consider three regimes for which these metrics make sense. First of all, in the regime where the symbol time is very small with respect to the coherence time. So that corresponds to the red vertical bars in the figure on top. In that case, outage probability is a meaningful performance metric. So again, if we go to the figure, we see that in the first case, all the symbols saw a good channel, while in the second case, all the symbols saw a bad channel, so there was an outage. So in this case, outage probability is a reasonable performance metric. If we want to reduce outage probability, we will use power control. So in case of the bad channel, if the receiver can report to the transmitter there was a bad channel, the transmitter can use higher power or a different modulation format to improve the performance. The second case is when the symbol slot duration is much larger than the coherence time of the channel. This is what is shown in yellow. So we see a symbol duration extremely long. In this case, the fading is actually averaged out during the symbol slot. So it approximately looks like an additive wide Gaussian noise channel with the average channel. And this is not considered here because it's not very interesting and not very relevant from a practical point of view. Finally, we have the case where the symbol slot duration is on the order of the coherence time, as shown in green. In this case, the average error probability is a reasonable metric, because when we send a sequence of data symbols, they will each see a different channel, and then the average is a meaningful way to quantify performance. If we want to improve average error probability on such a communication system, we will use diversity, which we will see in the next lecture. So the remainder of this lecture is on performance in flat fading. If you're interested to learn about performance in frequency selective fading, you will need to wait till the lecture on OFDM. We will now introduce three different notions of SNR and three different notions of power. First of all, we have the power due to path loss only. We denote this by PR bar bar, because there's two types of averaging that is done here, so we have two bars. This is just a standard path loss equation. K times the reference distance over D times, and now here this gets confusing, here gamma is the path loss exponent. With this average power, we can also consider an SNR, here shown on the right. So gamma S bar bar is the SNR due to path loss only. PR bar bar is the power due to path loss only, and null times B is the power spectral density of the noise times the bandwidth. Secondly, we have the power after shadowing. The power after shadowing in dB has a Gaussian distribution with a mean given by the power in dB due to path loss and a certain variance around that. So the power due to shadowing we denote by PR bar, so there's one bar here. The mean is PR bar bar, the power due to path loss only. And we can also express this as the power due to path loss plus a zero mean disturbance with the same variance. So with the shadowing power, we can also associate an SNR. The SNR after shadowing and path loss is denoted gamma bar S is equal to the power after shadowing and path loss, PR bar, divided by the noise power. Finally, after multipath, in case of the Rayleigh fading case, the instantaneous power is the average power after path loss and shadowing times an exponential random variable, or equivalently drawing an exponential variable like this. So the mean should be PR bar. So we can generate many realizations of the multipath with the given mean, PR bar. Then of course we have an SNR after path loss, shadowing, and multipath fading, which we denote by gamma S, no more bars, and this is equal to the received power after path loss, shadowing, and fading divided by the noise power. So just to comment on this averaging, the power due to shadowing here is the expected power after path loss, shadowing, and multipath fading in the linear domain. The power due to path loss in the dB domain is the average power due to path loss and shadowing in the dB domain, not in the linear domain. The figures in the bottom try to further illustrate this. Assume that we have a certain SNR after path loss only, gamma S bar bar, shown here on the right, in the dB scale. Then the power, or the SNR, due to path loss and shadowing will have a certain density, which is a Gaussian density with mean gamma bar bar S in dB. So then we can draw a realization of this gamma bar S, let's say a value here. This could be a realization of the SNR after path loss and shadowing. Once we have this realization, so once we have gamma bar S, we have an additional density of the SNR after path loss, multipath, and shadowing. So now on the x-axis you see here gamma bar S. This is the realization of the SNR due to path loss and shadowing. On the x-axis you see here gamma S, which is now a random variable with a certain density P of gamma S. This here is an exponential distribution. So the distribution of the SNR after multipath fading given path loss and shadowing has an exponential distribution. So if we want to draw a realization, we first compute the SNR due to path loss and shadowing from the path loss equation, generate a value from this Gaussian distribution in the dB domain, go to the linear domain, and then generate a value from this density here, and that gives us a realization of gamma S. Now with this, we can compute outage probability and average error probability. So again, outage probability is a probability that the performance falls below a certain threshold. For instance, that the bit error rate becomes above 10 to the minus 3. So this can often be written in terms of the SNR because we can relate bit error rate to SNR. So outage probability is a probability that the SNR falls below a certain threshold. We can then compute the outage probability depending on what this density is. So under Rayleigh fading, the SNR has an exponential distribution. So the outage probability is a probability that the SNR falls below a certain threshold. We can plug in the exponential distribution, which is done in the second step, and after some straightforward math, we find this expression here. So this is the outage probability for Rayleigh fading with a certain threshold gamma 0 and a certain average SNR due to path loss and shadowing, gamma bar S. From this outage probability, we can then in turn find something called the fade margin. This is the SNR that is needed after path loss and shadowing to meet the required outage probability for a certain threshold. So if you are given a certain threshold value and a certain outage probability, let's say 10 to the minus 5, then you can compute what is the requirement on the SNR after path loss and shadowing. So far we defined the outage in terms of the SNR after path loss, shadowing, and multipath fading, which had then an exponential distribution. We can also define outages as a function of the SNR after path loss and shadowing alone. In this case, the SNR in the dB domain will have a Gaussian distribution, and we can go through similar math. A second metric is the average outage probability. So we consider a case where during a certain time the SNR due to path loss and shadowing is constant, but many symbols are sent. Each symbol will see a different realization of the fading when we have fast communication. We can then compute the average symbol error probability as given by this expression. So we take the symbol error probability for a certain SNR, and this is from the tables that we've seen a few slides ago, multiply with the density of the SNR and integrate. So as a specific example, for DPSK, binary phase shift keying, the average error probability is here the error probability for a certain SNR, this is just a Q function, and then multiplied with the density of the SNR, which has as variable gamma and as parameter gamma bar S, the SNR after path loss and shadowing. After some simple math, we can find the following expression, which we can simplify approximately as follows. So the average error probability decreases as 1/4 over the SNR. This figure here shows the average error probability for BPSK in Rayleigh fading. So let's walk through this figure. The x-axis shows the SNR EB over N0. So this is the average SNR after path loss and shadowing. The y-axis shows the bit error rate. The light blue curves shows the performance for the additive wide Gaussian noise channel. Okay, so you can see this as having a certain SNR due to path loss and shadowing, let's say 5 dB here, and then communicating over an additive wide Gaussian noise channel over this 5 dB and having a bit error rate of this value here, maybe 0.008. The dark blue curve shows the performance under Rayleigh fading. So let's say again the SNR after path loss and shadowing is 5 dB. So we operate again in 5 dB. But now we have in addition Rayleigh fading, so the SNR becomes random with the average of 5 dB. And then our symbol error rate performance will be approximately 0.08, let's say. So a factor of 10 worse. So what is important to note from this figure is that even though the SNR on average is the same for the additive Gaussian noise channel as for the Rayleigh fading channel, the Rayleigh fading channel incurs a huge penalty, many tens of dBs depending on the operational bit error rate. So the Rayleigh fading channel is a very bad channel to communicate over compared to the additive wide Gaussian noise channel for the same average SNR. Let us now look at an example that combines outage and average probability all at once. So let's say we have an outage when the SNR due to path loss and shadowing falls below a certain threshold. When we are not in outage, so that means the SNR after path loss and shadowing is sufficiently high, then our performance metric is the average error probability. And here average should be considered due to multipath. Let's assume that we use BPSK signaling over a channel with Rayleigh fading and shadowing, where the shadowing has 8 dB standard deviation. The average SNR should be below 10 to the minus 4, most of the time 99%. So then how should we set the SNR due to path loss only to achieve the target symbol error rate 10 to the minus 4 99% of the time? Let's look at a proposed solution. For a given SNR due to path loss only, the SNR will vary due to two different effects, shadowing and multipath fading. Let's first look only at the effect of shadowing. So let's suppose we average out multipath fading, then here we have the variation of the SNR due to shadowing as a function of time. So this is the black line changing over time. The average value is gamma bar SS, at least in the dB domain. So this is the average value due to path loss only. This is the value that we want to set. So the red level is the level that we get to choose. We want to be above 34 dB 99% of the time. Why do we want 34 dB? Now I'll go back. we want an SNR of 10 to the, we want a symbol error rate of 10 to the minus 4. 10 to the minus 4 in this slide here gives us this value, which is about 34 dB. Alright, so this is said here in this second bullet. We want to make sure the gamma bar S is such that the average bit error rate is 10 to the minus 4, so we want gamma bar S to be more than 34 dB. Okay. And again, then this area will be less than 1%. So what we want is that gamma bar S is larger than 34 dB 99% of the time. We know that gamma bar S is a log normal distribution with mean gamma bar SS in the dB domain and a standard deviation of 8. So in the end, what we require is the following expression to hold. We want the SNR after path loss and shadowing, gamma bar S dB, to be less than 34 dB, only less than 1% of the time. Since gamma bar S has a Gaussian distribution, we then find, after some straightforward math, that gamma bar S in the dB domain should be more than 52.6 dB. So this tells us something for a given distance, how much transmit power, for instance, we should use. Finally, we will talk about the difference between coherent and non-coherent phase shift keying. Consider the following model, where we have an observation Rk, noise Nk, and now the transmitted signal is of a bit strange form. We only use phases, so this is the transmitted signal, where theta k contains the data. So bits are mapped to phases, as in NPSK. Zk is a complex channel, so this is a channel that varies over time. In coherent communication, we encode information in the absolute phase, theta k. So this works as follows. We have certain bits, we map them to NPSK, so then we have these phases. Then we send over the channel Zk, we add noise, we have an observation Rk. What we do is we have a whole bunch of those observations, and if the channel is approximately the same for all of those, we can reserve a few of those phases e to the power j theta k for pilot symbols. From pilot symbols, we can estimate the channel. This gives us an estimate, z hat k of the channel. Let's say this channel remains constant for a long time, and then we can recover the data using the maximum likelihood criterion. Now this is fine, provided that we can estimate the channel, and this we can only do when the channel does not vary too quickly. If the channel varies quickly, what we can do is we can encode information in the relative phase, so the differences between two phases. We do this as follows. We have our bits, we map them again as before to NPSK. So now these are NPSK modulated symbols. But then instead of sending these directly over the channel, we do first a simple coding. So this is a kind of coding on symbols. So what we do is we take the previously transmitted symbol and we multiply it with the current NPSK symbol, and that's what we then transmit. So this is again a point on the unit circle. It's a phase. It actually looks the same as an NPSK symbol, and we send this over the channel. So we have a simple code before we go into the channel. Then we apply the channel, we add noise, and then we have our observations Rk. So now we need to use a simple decoder to recover the information. What we do is we take a one symbol delay, take a complex conjugate, and multiply Rk with Rk star minus 1. And that gives us a new observation Yk. Let's consider the easy case where there's no noise. So what happens then? Yk is Rk times Rk minus 1 star. I can plug in what Rk means. So Rk is Zk times e to the power j theta k. Rk minus 1 star is Zk minus 1 star times e to the power minus jk theta minus 1. And of course, this guy here, e to the power j theta k minus theta k minus 1, is actually the data symbol that we're interested in. This was actually what we had here. This contains our data. Now there's this disturbance, Zk minus 1 star, but when the channel varies only very slowly over time, this is approximately a real number. Okay, so this is a real number, so we can ignore it when we do the detection. And this is true when the channel changes not too fast. It can vary every symbol, but it cannot be completely independent. Okay, so this here is a real number for a constant channel, so we can definitely ignore it. It's approximately a real number when the channel varies very slowly. then still we can use it, we can wipe it off to recover our data. Or when the channel is very fast, then it can be any complex number, and then this observation yk is useless to recover the original data. So this tells you that when the channel is varying very fast, we will have some error floor. We cannot recover the data. When the channel varies slowly, we can recover the data quite reliable. It turns out you can characterize this analytically for differential binary phase shift keying, in which case the average error probability will be given by this expression, where we notice the SNR per bit after path loss and shadowing, and also rho c, which depends on how quickly the channel changes. So rho c is the autocorrelation function at one symbol slot divided by the autocorrelation function at 0. So this value will be close to 1 when the channel is almost static. Okay, when this is close to 1, this entire thing here disappears. So we get 1/2 times 1 over 1 plus gamma bar b. Or when the channel is very fast, then AC of t will be close to 0. So then this guy completely disappears. This whole ratio will become 1, and the average bit error probability will be 0.5. We recall from a previous lecture that this rho c can be found from a Bessel function in the case of the Jakes model. So let's look how this looks like in a figure. So here on the x-axis, I have the average SNR per bit after path loss and shadowing. The y-axis is the bit error rate. And different curves correspond to different Doppler shifts, FD. So when the Doppler shift is 0, then the frequency Fm is 0. Then we basically recover the standard Rayleigh curve. This is this one. When the Doppler shift is very high, this value of Fm will be very high, then we see an error floor that occurs very quickly, so even for moderate SNRs. When the Doppler increases and increases, at some point the bit error rate will just be 0.5, so you will get a flat line for every SNR in your system. So we're ready to wrap up. In this lecture, we've seen different notions of symbol error rate and signal-to-noise ratio. We saw outage probability and average error probability, and we also discussed the differences between coherent and differential detection.